Flow with streams. So basically talking about loading systems. I think you all have notes on all of this. I think I put them online. Okay. Again, this is all review: flowing water, rivers and streams. And what makes them different than other aquatic systems is the fact that you do have movement, and for the most part unidirectional. And that becomes like the major, that sets all the other physical parameters for what's going on in these systems here. Okay, some different pieces and parts. If we look at a stream, these are just basically some terms. Okay. Well, first of all, where do streams begin? A number of different possible beginnings. A lot of them come out of springs, and what a spring is, remember I told you the movement of groundwater flow is moving, of course, following topography. And if the stream bed is deeper than the water table, you then have a spring. And that's where it comes. Where groundwater suddenly becomes channel flow, stream flow. You can also happen with subsurface flow as well. Overland flow often begins too. Overland flow tends to be a little more seasonal. I'll mention that in a minute here. As is snow and ice melt. And in a lot of places, especially in man-made systems, streams may begin at the outflow of a pond or a lake. And also you can find different wetlands here. This has interesting connotations on water quality. Outlets from wetlands are very different than other systems. The flow itself can be permanent. That's year-round flow. That's it. I'm not saying stable. I'm saying permanent. The stream is always flowing. It's going to change high, low throughout that. There's also intermittent flow. So these tend to be seasonal flow or storm flow. A lot of this are basically these categories right here. Intermittent streams, and I'll be talking about them a little bit later. Very end of the course, we start talking about pond management. Intermittent streams are basically what you look for when you're looking to build a pond. You don't build it on a permanent stream, you build on an intermittent stream. Okay. Here's some special stream terms. As you look around here, this is the upper end of the Wolf River in Fayette County here. So that's a good loading system that you're looking at here. And so this schematic basically shows the stream itself and has all these different terms in it. And you notice there's basically a boundary around this area. Everything, this is based on topography. Everything on the inside of that line would flow into these streams. Everything on the outside of that line would flow to another stream system here. The area declared by that boundary is called a watershed. Often another term that's used, you may see, is called a catchment. I tend to use watershed. Catchment is more of a European term. And so that is just all the land where all the runoff, and by runoff I'm using that term very loosely, subsurface flow, overland flow, groundwater flow, precipitation, everything collects into a common system. And usually, of course, that system is loading, but not always. Examples of that where it collects into a lentic system would be the Great Salt Lake and the Dead Sea. This is known as Lake Kinneret, depending on your proclivity. So in those cases, there's no outlet to those systems. So you have basically the watershed, and then the stream itself, the stream bed, and the banks within it form a channel. And this is a classic West Tennessee channel here. We will be in one of these on Wednesday. In fact, we'll probably be at that very site on Wednesday. Our stream channels tend to be deeply incised. They're cut in here. That is not a natural feature. That's from human disturbance. Okay, if you look at the stream, if I follow this little stream, I watch it, and it does this. It's here, back here, here, down, around, over here. Streams, if not constrained tightly by their channel, tend to meander. So these are stream meanders here. So basically, these are sort of bends in the streams. It's water, in the physics of water, have you ever laid a garden hose down on the ground and then turned it on full blast? See, what does a garden hose do? Just sit there and pour water? No, it whips back and forth. Water, constrained water tends to release its energy laterally. Okay, so what you see is that hose doesn't suddenly go straight up in the air. It slides back and forth. Well, that's what you're seeing in the streams. Basically, as that stream is, water's coming down that stream, of course, its potential energy is becoming kinetic energy as you go from a higher place to a lower place, and that energy is being released through meanders. So the streams, the more meanders you have, the more sinuous the stream is. And so often we measure streams in terms of their sinuosity. It is a natural feature to see streams with sinuous flow. Next term here, this little habitat here that you're looking at, this is called a riffle. So riffle is, you can see the disturbed water here. You can see a little bit of turbulent flow, but very, very light turbulent flow in this case there. Okay. It's a section of a stream where the water is shallow and relatively fast moving. Relatively fast moving, I'll explain that later. Okay. And as a result, you get some turbulence. So I see these little waves going here. What they're doing is they're putting in a rubber duck, running it through here to see how fast it goes down. Get some concept of velocity of the stream. So, well, what's causing those, of course, is the roughness of the bottom. Is causing the ripples in a riffle. This is a pool. And pools, unlike riffles, they tend to be more deep, and the water is moving much more slowly. So in this picture here, though you can't see it, there's a riffle above the corner here, which then is a nice shallow riffle up here, which empties into this pool. And if I follow this pool long enough, I start to get into another riffle again down here. That's a very common feature for streams. As you go from the upstream to the downstream, you have a riffle pool sequence. So riffle to pool, riffle to pool. We'll see that on Wednesday. Another term that's often used is called the riparian zone. And the riparian zone, because this is a back channel of the Mississippi River here, so this is basically, this is low water, but this is generally a flowing system here. So when it is any of the land or the vegetation that borders along a river is the riparian zone. So in my watershed map here that I drew, the riparian zone would be anywhere on the shore, on either side of this. A similar term, okay, yeah, it may or may not be intermittently flooded. Intermittently flooded should be an E on B, but it still works. Another very similar habitat to the riparian area, mostly these are associated with larger rivers, is the floodplain. How would you define a floodplain? Has that name, floodplain?
An area of land consistently covered by foot deep water at least.
Okay. So you called it an area of land consistently covered or intermittently covered by water. Okay. No. I said that because I know that's what you've all been taught. Floodplain is, and I'm going to break you of that thinking. Okay. It's an intermittently flooded area along a river. And you're thinking, isn't that what I just said? And the answer is no. What you told me was it's land that's sometimes flooded. That's not how I think. That's not how a river ecologist thinks. We don't think the floodplain is land. Floodplain is river that's sometimes dry. That little change in thinking right there makes all the difference in understanding rivers. Because the way you describe it, the floodplain is land, and therefore, you can protect it from the river. And I'm saying the floodplain is river, and if you separate it from the main channel, that's why we get in all the troubles we get in. Okay, so here's a stream. One about this basically that's what I showed you, the Cane Creek before, that deep incision in there. This is the same place. Only now we're looking down. We're not in the stream for obvious reasons. But if you look at the stream now, it fills the entire incision from one side to the other side. This river is at what we call bank full width right now. So that's where the water completely fills the channel, okay? And if there were any more water in it, it would spill out into either the riparian zone or the floodplain. It's not gonna take much more for this river to come out of that. We'll see, one feature that's often measured by, when you go to a stream, is you measure its bank full width. And to do that, usually it's evident, you can see it by the vegetation line. We'll show you bank full width on some of these streams we'll be playing around in. Turbidity, since you have a moving system, we know that moving water is erosive. Because it's erosive, it tends to carry a lot of it. This is back to that idea of suspensibility. You can suspend a lot of material in it. So turbidity are the particles suspended in the water. And those particles in there, they have a number of different effects. One of their effects, of course, is light attenuation. Light can't go down, and so greenwood's algae are in real trouble in these sort of systems. And there's lots of other things that have to do with a stream. Well, I plan to give you a whole lecture on stream turbidity, talking about turbidity in aquatic systems. Associated with that is what is known as siltation. So basically, so if I have a moving stream, I mean, I know that the stream is moving and is carrying material. When the stream is out and it gets out of the main channel, speed drops. And when the speed drops, it can't carry as much. And so you get deposition of those fine particles. And they can either be deposition in some areas inside the stream, or in this case here, it's deposition on the outside of the stream. I don't like the term siltation, okay? It's kind of a misnomer, because this is siltation, so you're thinking that this is silt. This is not just silt. Okay? Silt is a particle size. Sand is a particle size. Clay, gravel, pebble, cobble. And if I'm looking in here, I'm seeing, besides silt, I'm seeing clay, and I'm seeing some gravel in here. And so these all fell by siltation. So instead of using siltation, we often use the term sedimentation. It's a better way to describe it. Sediment can be also all particle sizes. I'm going to be talking about particle sizes later on. Probably now we're going to get to some of the big things that define stream systems. One is velocity. And we've already mentioned velocity. We're doing some measurements of velocity. And that's just basically the distance of water moved per unit time. Just like on your car. Your speed of your car is basically the velocity. How many miles does it move per hour? We don't tend to measure stream velocity in miles per hour. It would be a very low number. Okay. Here are some of the standard units that we use. Probably the most common one is meters per second. So that works in most normal sized streams. Feet per second, if you're dealing with some of the federal agencies haven't switched over to SI units, and they still measure things in feet per second. So what affects velocity? So let's say I'm going to focus on it for a little bit here. A number of things will affect velocity. And a lot of those things are the very features of the channel itself. For example, how wide is the channel? So again, if the channel is wide and not constrained, velocity is usually pretty low. If the channel is constrained, if it's shaped, if it's tight, it's like back to my analogy, if I have water running out of a hose, it's just running out of the hose, that's fine. But if I put my finger over it and make the aperture smaller, then velocity shoots way up. So you can affect the velocity just by the shape of the channel. Of course, gradient makes sense. Low gradient is how far the channel falls per, how much drop is there per run of the stream. It's the slope of the channel, what you're looking at here. If the gradient is high, the water's going to be moving fast, it's going to affect it. Gradient low, it's going to slow things down. Some of the other factors are if you have a very smooth channel, like storm drain or something like that, velocity is very high because energy is not being lost to the roughness of the channel. In rough channels, like you tend to lose things. That's why whenever you want to if you've ever gone by a river, do you know what the term riprap means? No. Okay. So if you look on, oftentimes, stream systems where they have a bank that's eroding, what they'll do is they'll drop stones, lots and lots of stones of different sizes onto that and increase the roughness. Those stones are called riprap. And riprap then is the purpose is to increase the bottom roughness, and that drops velocity, so the stream is less likely to erode away materials. Depth has an effect. The deeper a stream is, it appears, a lot of times very big rivers appear to be moving slowly. They're not. They're just the faster water is moving deeper down, because the water at the surface doesn't move as fast because it has friction against the air. The water deeper down, usually about 60 to 80% depth, is moving very fast. Okay. And of course, the amount of precipitation in the stream is going to affect velocity simply by affecting volume. Another term, and I mentioned this term before, is discharge. So discharge, and again, it uses the symbol Q, that's universal. Discharge takes into account how wide the stream is, how deep the stream is, which basically then gives us a unit of area. So if I look at a stream, if I know how wide it is in general, how deep it is in general, I can measure that in square meters. Then I can put in another parameter, and that's how fast is the velocity moving by. So if I've got area in square meters, velocity in meters per second, multiply those together, discharge then, so if I take the width of the stream, meters, depth of the stream, meters, velocity of the stream in meters per second, discharge is then measured in cubic meters per second. This is a common way to do it. Again, cubic feet per second is used. And on little tiny streams like Cane Creek, especially Cane Creek, where we go there on Wednesday, if we don't get rain, it's going to be a real easy day because there's not going to be much water movement. That you would measure in liters per second. So discharge is units of volume per time. All right, so in stream systems, basically, if you're in a stream, especially smaller streams like this one here, and we talk about smaller and larger streams and what makes the stream size. Okay, so this basically here, this is a stream in western North Carolina. This is called Coweta Creek. So this is very, very close to the area where both Dr. Greenwood and I did my research, did our research. The research that Dr. Greenwood did feeds this stream. It's a small tributary to the stream. I did my research in this stream and in the Little Tennessee River, but we're farther down. So basically, if I walk down that stream, I talked about the fact that you go through a riffle habitat, and then you go through a pool habitat. Riffle, pool as you make your way down. You move between fast water habitats and slow water habitats. Now there are different kinds of fast water habitats and different kinds of slow water habitats, but you still get that riffle pool sequence. So let me talk about what defines a fast water habitat first, okay? In general, the rule of thumb is the flow is greater than 50 centimeters per second. In other words, the water is moving at 2 meters, at a meter every 2 seconds, which should probably be something like about this, meter every 2 seconds. So that's one thing about it. Okay. These tend to be areas of erosional zones, okay, because the water is moving fast. We know that increases its suspensibility. So the particles get picked up. The smaller particles are going to be moved out. And what that's going to leave, it's going to leave these standard particle sizes here. So I put the particle sizes in order here on the board so you can see what they are. So the largest of all particle sizes is bedrock. Okay. Bedrock, cobble, or boulder. Hard writing there. Cobble. Pebble. Gravel. silt, and clay. So if I'm in a fast-moving habitat, clay, silt, sand, gravel are going to be moved out. Primarily. That's going to leave pebble, cobble, boulder, and bedrock in these systems here. The flow, and you can see it right here. You can see how these are all. What you're looking here is primarily boulder, some cobble here, in that system there. I'll talk about it. So, I guess so. Basically, clay kind of feels like when you feel clay, it feels greasy. Particles are so small. Silt feels like cooking flour. Sand of course is gritty, and note the size. No angle is greater than 2 millimeters. Gravel, of course, is a little bigger than that. Pebble, bigger than that. Cobble. What separates pebble from cobble is all these have real numbers to them, but if you're in the field, you don't sit around and measure every rock. You pick up cobble and you look at that. You pick up the rock and look at it, and you say to yourself, that fit in my mouth. You don't actually put it in your mouth. If it'll fit in your mouth, it's pebble. If it won't fit in your mouth, it's cobble. Okay. Can I pick it up? It's cobble. Can I pick it up and hate my life? Yes, it's bedrock. It's boulder. Okay, boulders, you really can't really pick them up. Maybe you could, but you're not going to want to. So that's basically how we do that. It's done by feel. Anyway, these are areas of turbulent flow, and as a result of turbulent flow, there is plenty of oxygen, high dissolved oxygen in these systems here. So, if you're a critter that is good at holding itself in place, this is Fat City. This is a wonderful habitat to be in. Okay. So the names of some of the habitats. So we have what are called runs. Runs would be the slowest of the fast water habitats. So runs, the water's moving, but the turbulent flow isn't all that turbulent. Riffles, of course, we just explained those. You do have clear-cut turbulent flow. And then sort of the grandmother of the whole thing are the cascades. Cascade is just the proper term for a waterfall. So, extremely high areas. So again, if you can hang on to these areas here, if you think about it, if you're a little critter that can hold its place, it's got all the oxygen you need, and food is constantly coming by you, because you got all this suspended organic matter. So you just reach up and grab your food. It's a great place to live if you can hold on. This is a slow water habitat right here. And again, I showed this picture because you can see this is a pool. Here's a riffle here. There's a riffle above it, and there'll probably be a pool over here. It's a very common feature of stream systems, especially in the southeastern United States. And if you go to eastern Kentucky, western North Carolina, you see these riffle. There's even riffle pool sequences here. But it's a very common feature of small streams. So again, easy flows, less than 50 centimeters per second. These tend to be depositional areas. Material is fun. So you've just come across this riffle up here. You've got erosional things going on that material. You hit slow water, you're going to deposit. And what are you going to see primarily? Gravel, sand, silt, and clay, depending on what's coming out here. The water is not turbulent flow. It's basically kind of laminar, moving slowly. And dissolved oxygen can become a real problem. It's not, you don't have any problem at all holding yourself in place. There's plenty of things to eat because everything's falling down on the bottom and all that organic matter is coming down. So if you want to walk around and eat little things, you can find it. But dissolved oxygen is going to become a real problem if you're not, because basically oxygen is going to be being taken up by bacteria and other living things in there, and you don't have the pump going. You're not disturbing the water enough. Examples of these habitats are pools like we talked about, side channels, glides, and sloughs. A glide is probably the fastest of these sort of habitats. It's the break between a glide and a run is very, very, you can see some movement, but it's basically, it's cut off right about here. It's moving close to half a meter a second, but it's not. So glide would be the fastest of those habitats. Pools would be the slowest. Okay. Here's another one, a bayou. Okay, have you heard this term bayou? Okay, and you heard me talk about, you had lessons with me, right?
Mhm.
Okay, so you already know the secret of bayous. Okay, so, can anyone name a bayou? When you think of a bayou in the world? Never been?
Think of like Louisiana area.
Lots of them in the Louisiana area, and those are true bayous. But if you were to go from Fulton, Kentucky to Mayfield, you pass Bayou de Chene. And they use the term bayou, it means the bayou of dogs. Okay, in case because you really cared about that. But anyway, but it is not a bayou. It's not a true bayou. Okay. So look at my drawing here. Okay. These are streams that are coming together to form a bigger system. Okay. So these are called tributaries. When I get down to the area Caitlin was talking about, get down to Louisiana, the opposite's happening. The main river is going through distributaries. They're spreading out across the delta. That's a bayou. A bayou is a distributary. It is not a tributary when properly used. And these tend to move very slow. This is a bayou near Thibodaux, Louisiana, right here. I went down to, I was offered a position at Louisiana State and went down to look at it. I didn't take it. All right. So channel feature size, okay. Size is important. So I've been talking about, so big streams, little streams, all that sort of stuff, that's kind of important. Let me check my time before I get too involved here and keep you for a million years, which I will hope to find. Since I take my hike here. One way of measuring, there's lots of ways of measuring stream, how much water it carries, how long the stream is. But one of the common ways of measuring streams is we can give them a number. Okay? And this is called the stream order. Okay, so stream orders. Okay? And again, streams join together by tributaries. This tributary joins with this tributary to form a little larger system. And this system here joins with this one to form a larger system. And these two areas form a larger system. Okay? And the way it works is every time is that as streams come together, but there's an important rule here. As streams come together, streams are given an order number, and that order number changes whenever two streams of the same order come together. Okay. So, if you look at my picture here, I have these streams. Back down to part of that stream. Okay. I have streams that another stream doesn't feed it. This one here, this one. They're basically headwater streams, springs coming from something else. Each one of those is a headwater stream. Okay? Each one of those is what we call a first order stream. I'm counting up how many I have in my picture. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Looks like 13. Got them all, right? So in my picture here, first order, there are 13 examples in this picture here. Okay. A stream can only increase in stream order if a stream of a similar order joins it. Okay? So this is pretty easy to figure out. So first, it's a first. So right here, I'm at a what? That's a second. First, second. First, second. Wait, that's so far. Try to count 1, 2, 3, 4, 5. Okay. See, now this is now a second order stream. When the second order stream gets hit by a first order stream, it's still a second order stream. It doesn't get to change. So this is still second order. Comes down here, it's still second order. It's second order all the way down to here. Okay, so I'm going to have 1, 2, 3, 4, 5. So second order. Order is not just increase when the lower joins a large order. Okay. So let's continue here. So here's a second order stream. So we have, this is the second order stream. This is the second order stream. They come together, boom, right here. I now have a third order system. So I know we're going to have third orders. So I've got one so far. Here's a second order hitting my third order, nothing happens. Second order hitting my second order, right here. This is a second, this is a second. So eventually they're going to hit right here. I get another third order. So in my picture here, I have two third order streams. And when they come together, right down here, this third order, I have one fourth order stream. One, not four. So, going from 13 first orders, 5 second orders, 2 third orders, 1 fourth order. This does some really interesting things, okay? So, generally, the general rule of thumb is first through third order streams are generally referred to as headwater streams. They're very small systems, very tiny systems. Dr. Greenwood did most of her work on a second order stream. See, I think it's, which branch, Cunningham branch, I think. Okay. Fourth order through sixth order streams are generally called medium-sized streams or small rivers. Anything at sixth order is a river for sure, and if you're above sixth order, you're known as a large river. Mississippi's around a 9. No one has any idea how big the Amazon is because you can't count all the headwaters. Okay. So, if you think about this, especially if you think about where most of the stream work that was done, it's not by happenstance that Greenwood and I came from the same place and happened to both be stream ecologists. All of the work on stream ecology came from the southeastern United States. And the big schools were Alabama, Georgia, and Virginia Tech. That's where most of the research came from. And so we were Georgians. So anyway, and if you look at those streams, the lower order streams were way up in the mountains, coming out of the Smoky Mountains where we were at. In Virginia Tech, same sort of thing, Smoky Mountains and Appalachians. And Alabama, Alabama came over to work with us primarily. And then another general thing is, so they're way up there, and as you come down, the gradient starts to drop, and these streams start having large floodplains. So up in these little headwaters, there is no real floodplain. The water hits it, stays in the channel, flows down the channel. As I get bigger and bigger, then eventually I start getting into a floodplain. So I just did that whiteboard, okay? So now, the interesting thing is, if you're doing research, if you're doing an experimental design, what is an important component to have an experimental design? You're doing an experiment, what?
Control.
Controls, okay, so I want my streams to all be the same size, the controlled, everybody's the same. What's the other important thing? Replication. So you're studying the stream, and you want control and replication. What size stream are you going to use? You're going to use first order stream. I got 13 here. One I can forget about. I got 12 streams. I can increase the amount of I can do a Greenwood study. I can increase the amount of nutrients in 4 of them. I can leave 4 of them plain, and the other one I can decrease nutrients, and then look at the impact on those streams. And as a result, most studies of loadic systems come from headwater streams. So that's what we think about. Okay, so what we know, all of our ideas of loading systems, all the paradigms, all the hypotheses, and even a couple of important concepts were made up in small streams and then applied to all systems. Okay, so again, this is a perfect example here. This is actually a fifth order system. And that's gonna be pretty busy to get it up there. So it's fourth order here, it's fifth order down to here and here. So I go to a sixth order system flowing into a lake. If I want to study sixth order systems, I couldn't. I only have one. Okay. Well, why don't you study, can't you just study it in 12 different places? Anybody know why not? Your statistics people are failing you if you can't answer that question. Okay. Why can't, so if I need to take, why don't I just set up 12 sampling sites on this sixth order stream?
Because no matter how many samples you set up, it's still the same stream.
Thank you. So what do we call that? And you see it all the time. I'm a stream person. We do that crap all the time. It's called pseudo-replication. So, but if I, again, stream people who work on larger systems end up having to do that a lot. And it's all your data are always questioned because that ain't science. Okay? So why do we usually study headwater systems? First of all, easy to operate. Okay? So I want to measure the width of the stream. That's really pretty easy. You can just straddle it and put down a ruler. Okay? Can't do that on the Mississippi. Okay? It's even tough on the Obion. Okay? The availability of replication, wonderful, wonderful thing. Okay? The lack of perturbation. Okay? Remember how people come into the world or into colonize new places. They start where the rivers hit the oceans and they work their way up. So you end up with large rivers have been heavily manipulated by humans, so you can't really understand how they work naturally. So while the headwater streams, you get up in those mountains places where they haven't had much perturbation, and you can deal with that. But then the nagging question is, are rivers really just small streams? Do the same rules apply? What's going on in a small river, does that really apply what's happening in large rivers? Okay, and I said I'll get to that in a little bit later, because I'm probably going to have to go for a couple of lectures on this stuff. Okay. So another characteristic when we talk about rivers, by the way, is it's their physical form, how they move through the landscape. And this is known as geomorphology. Geomorphologists are just people who study the shape of the land. They're geologists who are into shape, geologists and geographers that are into shape, and geomorphology. So basically understanding the physical form of rivers is kind of important. What is the shape of the channel? What's the form, bank features? This is the geomorphology of this river is highly sinuous, meandering system. So along with the geomorphology, it's basically three things that are going to be playing in with each other. So geomorphology is the material that the river is coming through. Gradient is how fast that river is dropping. Okay, so it's slope. And the third thing is discharge. And so basically these three things affect each other and are determined by each other. That if my gradient is high, it's going to increase discharge. Okay. If geomorphology is such that the river meanders, it's going to slow discharge. And so these things work on each other. So basically there's just an interplay. What decides what a river is going to look like is based on its geomorphology, discharge, and gradient. Okay. Example of that. Okay. So geomorphology and high gradient rivers, so they tend to be heavily constrained to a small channel, fast moving water. If I get down as that river, so these high mountain streams, up with those first order streams, that water is moving extremely fast. It's going from here to here quickly. As it gets down and the rivers get bigger and the gradient starts to break, we start to get the channel, and this channel is very, very defined. It is a single channel, water moving as fast as it can down here. But as the gradient starts to change, then my river no longer has a single channel, it has many channels. It starts to braid, is what's called, move down here. And then if I get flatter still, that's when I get this river just sliding side to side all the time. So So basically, this is geomorphology affecting all these these different river gradients. I want to do a quick focus on large rivers. I mean, it ain't all that quick. I want to talk about this idea: are large rivers just simply big first-order systems? So I'm going to stop there because my background is there's not a whole lot of us in the world. I'm a large river ecologist. And so I worked for many years on the upper Mississippi River, then worked for many years on the lower Mississippi. So I want to talk about large rivers because this is a major feature from us here. And I'm going to stop there for today.